Okay. Hello everyone, today I'll be presenting our discrete project which is analyzing economic relationship between Pakistani cities using CPI data. If I were to tell you guys about CPI, CPI is Consumer Price Index which tells us how prices of everyday items change over time in different cities. It is basically a measure of inflation and cost of living differences across Pakistan. Our main goal was to go beyond just looking at raw numbers and actually understand how similar or different price movement patterns are between cities over a span of 2 years. During we treated each city's monthly price changes as vector, then used cosine similarity to measure how close their price trends match. The higher the similarity, the more synchronized their markets are. We then built the dynamic networks or graphs with cities on nodes and edges appears when two cities have very similar price patterns. Finally, we use weighted centrality measures. We rank cities to reveal a clear hierarchy. With this approach, let us visually and mathematically see how economic connections between cities strengthen or weaken over time.
Hello, this is my discrete project part 1 I would like to explain, which is mathematical modeling. Mathematical modeling basically explains the steps taken to transform the CPI. CPI means cost price index data, which is a large data having prices of each category and items under that category of a particular month of that particular year into network based structures. It is basically a precise rule which constitutes a node as a city and sharing item with other city as edge. It converts the complex data into structures or cities acting as a bridge. Basically, the benefits are to identify the convergence of price, similarities, sharing how much with other region, and isolation if there is any between two cities. For this case, I used first of all pre-processing technique for the Excel files which I downloaded from the links which was shared by the sir. I normalized it using the code of Python, which is this one. I used the dictionary data structure for category, having the different categories and the items falling under that category are stored in this array. I used the code for extracting the data and normalizing it, then merging into single Excel file large one. After that, I used cosine similarity technique, which is the formula is given. This is it basically tells how much city is closely related to other city in terms of price vector. And similarity threshold also set upon. Higher the value of threshold creates a sparse network, which means the strongest network is sharing between other city. Here is the code for similarity computation. Then I built the graph and the different thresholds. The standard threshold I used is 0.95, and then centrality matrix I computed, which tells us how much city is connecting to the by means of eigenvector and how much central the city in terms of price. Here is it for 2 years and for different categories we see Probability of degree is 1 and betweenness is 0 for all the 11 cities and 6 categories, but for utilities we see that there is less connection between cities and betweenness. Centrality is also non-zero, which means it is acting as a bridge. We can also see from here as well as for this tells us that the utility is sharing no connection under different tiers, while other categories are sharing a connection with other tiers. Here is the matrix I computed, and here is the network graph. Thank you.
Weighted centrality analysis, aggregation, and interpretation. Our main goal was to take four different influence scores for each city, degree, closeness, betweenness, and eigenvector, and combine them into the one strong influence score S. This is defined in section 1.1. The problem in redundancy scores like eigenvector and like degree and eigenvector often measure the same thing. How connected a city is. If we just average them, we introduce bias and make the score unfair. We need mathematical proven weights WK to fix this. This leads us to our advanced technique, the entropy-based weighting formula, shown in section 1.2. This method uses information theory to find the fairest weight. So let's talk about the weighting schemes. We use two schemes, a baseline and a corrective method. First of all, equal weighting baseline in section 2.1, we gave all four scores a natural weight of 25% each. This gave us our starting rank. The city ranking you see in the figure 3 is based on this equal score. Uh, Another one was the advanced method entropy-based weighting. Our main finding uses the entropy-based weighting in section 2.2. The logic is simple. If a score is almost the same for every city, it's not useful and gets a low weight. And if a score is very different for each city, it's the best way to tell cities apart. So it gets a high weight. The math showed that the brokerage rule betweenness had the highest variability, so we gave it the highest weight, 38.5%. This proved the brokerage rule is the most important factor. So moving on to the implementation, this complex math had to be translated into the working code, which is shown in the section 3 implementation. The code snippet shows the function we wrote, safe entropy weights. It handles all the steps. First, it normalizes the score, then it uses logarithms to calculate entropy, and finally, it calculates the fair weights that sum up to